All right, we'll begin. Happy Monday, everybody. It's week 9. We're coming to the end of fall quarter rapidly. So we'll continue on. We introduced hierarchical models, and so these slides are all from Friday's lecture, and so I'm just going to cycle through all of these, okay? And what we're going to do is we are building this hierarchical model, okay? And in the hierarchical model, what we're saying is that this is kind of our design, is as far as the data goes, the data are generated from a Bernoulli distribution. Each player has their own batting average. Each player has a batting average. So player 1 has theta 1, player 2 has theta 2, player 3 has theta 3, so on and so forth. Each player has their own batting average, and their values are generated from Bernoulli distribution. So perhaps player 1's batting average is 0.25, and we generate hits and outs with a probability of 0.25. Player 2 might have a batting average of 0.28, and we generate hits and outs based on 0.28. Player 3 might have a batting average of 0.20, and we generate hits and outs based on that. These different batting averages, these different thetas, come from a beta distribution. The beta distribution has a prior distribution. That prior distribution is defined by the shape parameters alpha and beta. So we use these two shape parameters to determine the beta distribution. And what we're doing in this hierarchical model is, rather than just specifying what alpha and beta are kind of manually, is we are saying these values, alpha and beta themselves, come from a hyperprior distribution. They come from another distribution, and this distribution uses, in order to kind of control how it is, and just so we don't have too many parameters, we're using a single value omega being a value between 0 and 1, omega kind of determining where the peak of our beta distribution is. And with some algebra, using omega, we can recover what alpha is and what beta is. So using omega and just some constant k, and here we've just arbitrarily selected k to be 300. Someone else could use a different k, but here we're just using k equal to 300, and using k in conjunction with omega, we can get back a value for alpha and get back a value for beta. Okay, and it's kind of close to omega times k and 1 minus omega times k. It's just plus or minus a couple of constants in there so that the values are correct. Okay, so once we draw a random value of omega from this hyperprior distribution, we just use a little bit of algebra to figure out what alpha and beta are. And once we have that, we generate each player's theta value, and with each player's theta value, we generate their actual sequence of hits and outs. And so this is our hierarchical model. And so what we want to do is we want to perform Bayesian inference on kind of all of the data that we've observed. Our data being all of the hits and the outs that we've observed. And here I've got 10 players. And so we have a total of, we're going to say 11 parameters to estimate. We got one theta value for each player. We've got 10 of those, 10 players here. And then we also want to estimate what omega is. Okay, and again, what we're going for is a posterior distribution based on the data that we've seen. Okay, the other parameters, k, a sub omega, alpha sub omega, and b sub omega, are arbitrarily selected. We're not going to do any inference on them based on our data. So using kind of Bayes' rule, we say the posterior distribution of theta 1, theta 2, up through theta 10, and omega, based on our data and these arbitrarily selected parameters, can be factored into the distribution of the data given these parameters, theta 1 through theta 10 and omega, times the prior distribution of theta 1 through theta 10 given omega. And because we divide by the marginal, which is a constant, we're just going to say it's proportional to this, and the product of these two things is just kind of the joint distribution of everything. And with the hierarchical model, the vector for one player, y sub 1, depends only on that player's batting average. So this joint distribution can be factored into this. We've got y1 given theta 1, the vector y2 given theta 2, so on and so forth, okay? And then we have kind of the distributions of each of these theta values, theta 1 given omega and k, theta 2 given omega and k, right? And this finally gets us to omega given the hyperprior parameter, the a sub omega and b sub omega. So here's the product of all of these things, okay? And just kind of rearranging things. Omega and k just translates into alpha and beta, right? Just via an algebraic relationship. In a deterministic, this is not random, okay? This is it. If you have omega and k, alpha and beta are determined. And so this is what we have. And so this is what we will calculate here. Okay, so each row is this, okay, or each kind of the total distribution. Each row in y is the result of random draws from Bernoulli distribution. Each player's batting average theta sub s is a random draw from the beta distribution, and the value omega is a result of a random distribution from a beta distribution. Okay, and these are the kind of hyperparameters there. Oh, we don't need the k here. So what we're going to do is we're going to create a Gibbs sampler that takes advantage of this structure. Okay. So here again, the goal of the Gibbs sampler is we want the resulting distribution. Okay, we want a sample of values from this resulting distribution over 11 different variables. Okay, so we've got the 10 theta values plus the omega value. And so this thing, when we're just trying to sample a value of theta sub s, okay, so say theta 1, we really only have to draw a value from this posterior distribution. Okay, the posterior distribution of theta 1 is going to be proportional to the distribution of basically our data times its likelihood. So y1 given theta 1 and theta 1 given alpha, comma beta. All right, let me pull up this here, okay? So if we take a look at each of these things, right, we already know kind of from earlier in the course when we talked about the posterior distribution of the unknown parameter theta given our data, we just update our beta distribution. We take the prior alpha and we add basically the number of successes, and we take our beta and we add the number of failures. Okay, so we do alpha plus the sum of our y's, comma beta plus the number of failures, which is n minus the sum of y's. Okay, and so this is the posterior distribution of theta, and we can just sample from this. So let me show you. text a little bit bigger. So we will run the Gibbs Sampler here, okay? And then let me show you how this this works. Okay. So here I'm going to just set an arbitrary seed. We've got 10 players, and we've got our imaginary batting averages. So this is the batting averages for our 10 players that we are going to use to generate our our data. Okay. So this is, and then I'm going to just say, I'm going to also allow for the number of at-bats to vary. With a mean of 500, we've got 10 different things. So the number of at-bats, so some people had 520 at-bats, and some people had, 486 or 493, okay? And here I'm just generating my Y matrix. Okay, non-numeric matrix extent. Sure. Okay. And so here I'm just generating my hits here. Hold on, am I doing something wrong here? Okay, I must have done something strange. Okay. So let me just show you what Y looks like. Okay, Y is a 10 by 521 matrix. Let me just show you. Y, let's look through the first 10 rows and first 10 columns. Okay, and so this is just a sequence of hits and outs. So player 1 just had out, 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 a whole bunch of outs, okay? Player 4 was off to a great start, okay? And we can kind of ask, all right, what are the row means of Y? This is kind of, all right, so these are the observed batting averages. Let's round this, of our data. Okay, these are the observed batting averages, and these were generated using this. Okay, so when we generated the data, we said player 1 has a batting average of 0.252. Now, it's random, and we had player 1, I don't know, have something around, player 1 had 486 at-bats, and out of 486 at-bats, player 1 had a certain number of hits, and so his empirical batting average, based on his 486 at-bats, is 0.243, okay? And so some people outperformed, right? So when we generated the data, we said their imaginary batting average is 0.275, and player 2, their actual performance was a little bit higher. And this is all just due to random chance. Okay, so this is what we have. And basically, Y is just this matrix of a whole bunch of zeros and ones, right? And it's and there's some missing values because some people had more at-bats than others. Okay. Now, what we could also do is we can just take the row sums and the number of at-bats, and so we can see player 1 had 118 at-bats out of 118 hits out of 486 at-bats. And so if you do 118 divided by 486, this is where you get that number, 0.243, okay? And so these are their number of hits, and this is the number of total at-bats that they had. So, all these players had slightly different numbers of at-bats. Okay, so how is this going to work? Well, we're going to do the Gibbs Sampler, and so I'm going to say we're going to do 15,000 iterations, and I'm going to have I'm going to keep track of all of the different thetas that I have. I'm going to have 15,000 rows because I'm going to do 15,000 iterations with 10 columns because I've got 10 different theta values to keep track of. And I'm also going to have a place to store all the different omegas that I've sampled. For my A sub omega hyperparameter, I'm picking a very wide, I'm going to choose A is 3 and B is 7. So that puts an average of around 0.3, but it's very, very, very wide, right? Because the sum of 3 and 7 is 10. So it's quite widespread. We're going to just arbitrarily select K to be 300, and I'm just arbitrarily setting omega to be 0.27. Okay. And so when we do our Gibbs Sampler, remember the Gibbs Sampler says reduce the joint distribution of everything. So our joint distribution is y, comma, theta 1, theta 2, theta, all the way through theta 10, comma, omega. The joint distribution of everything, factor that into a whole bunch of kind of univariate distributions and sample from those. And so each univariate distribution is basically, okay, what's the posterior distribution of y given theta times the prior distribution? And so what we know is that posterior distribution is just theta comes from a beta distribution where we do alpha plus the number of hits, comma, beta plus the number of outs. Okay, and so we are putting that in here. We've got, based on our current alpha and omega values, based on our omega values, omega and k values, we can calculate what the corresponding alpha is and the corresponding beta is. And here we're going to just sample one random value from the beta distribution where the shape parameter is alpha plus the number of hits for player S and beta plus the number of outs for player S, the number of outs being n minus k. And so this will give us one random value from the posterior distribution. Is that okay? For getting these theta values. And so we put that in there. Okay, now what do we do about the posterior distribution for omega? Okay, the posterior distribution for omega is more complicated. Oh, before I forget, let me give you first view quiz answer. Today is D. D as in dog. D as in dog. So the posterior distribution for omega is more complicated. We've got to figure out what is, after seeing all of our data, can we update the distribution of omega? Okay. Well, we'll use the Metropolis algorithm here. The Metropolis says, okay, well, the posterior has to be proportional to the likelihood times the prior, and we're not going to worry about the denominator. Okay, because the Metropolis algorithm, we only need the numerator part. And so we've arbitrarily selected for the hyperprior distribution of omega, we've selected shape parameters 3 and 7. Okay. K is arbitrarily selected to be 300. And so the posterior distribution, okay, is going to be proportional to the likelihood of our data, which is all of this. Okay, this is all of the data that we have, and then multiplied by the prior distribution. So our prior distribution is omega coming from this hyperprior with shape parameters 3 and 7. And remember, we need, okay, well, what's the likelihood of our data? Y given theta. Okay, y2 given theta 2, y10 given theta 10. And then these thetas themselves are determined by A and B, which themselves are determined by omega and k. So we'll get this. what's the probability of y given theta, this is equal to the binomial PMF, right? Binomial probability. We're going to say what's the probability of getting the k, which is the sum of the y's, and n, the number of observations given our current value of theta. All right, we're going to do this for every single player. So we do this for player 1, player 2, so on and so forth. And then we ask, what's the probability of getting theta 1 given alpha and beta? So we first calculate alpha and beta based on omega and k. And then we say, what's the probability using the beta density of this particular theta value? We do this for every theta. Theta 1, theta 2, theta 3, up to theta 10. And finally, we ask, what is the probability of this particular value of omega? Okay, and this will come from the beta PDF using the hyperprior parameters 3 and 7, a sub k and b sub k. Okay? Now, this is going to be a huge product, so instead of taking the product, which is going to give me a very small value and I could run into underflow errors, I'm going to take the log and add them up, and I'll just get a very negative number, but that's fine. So here is how I'm going to calculate this probability. So we're going to ask, what's the probability of omega given kind of the k and the thetas, and then the k and the n, I've got a vector. Remember, I've got a vector of hits and vector of at-bats. Little k and little n are found in the global environment. Okay, so this is not best practices where you're referencing objects in the global environment in your function, but that's what I've got going on here. Okay, so we're going to say, all right, what's the log probability of some value omega? Okay, for this thing, and so this is going to be used to calculate. So this function is proportional, at least to the log of this, right? So we're going to do d binom of kn theta, and we're going to say, give me back the log probability. Give me d beta of theta and alpha and beta along with the log. And then we're going to ask for the beta probability of omega given alpha omega, beta omega, and we want the log probability. We're going to add all of these things up. Okay, so this is what we have. Does that kind of make sense? What we're doing here? We're turning all of these into logs. We're going to add them all up, and we're getting these using our values here. So this is how we're going to evaluate kind of the posterior probability here, the likelihood. And what we need is this. Okay, we need a proposal function. All right. So we have our current value, omega, and again, what we're trying to do is we're trying to generate a sample of omega values from this posterior distribution. So using the Metropolis algorithm, what that requires is that we have to create a proposal function. We have to propose new values of omega. And so the new values of omega that we will generate is we're going to, I'm going to just say, propose a new value using the random normal centered currently at omega and just some arbitrary standard deviation. Right now it's set to be 0.05, but it could be something else. Now if it proposes an omega that's greater than 1, don't just use 1. And if it proposes an omega that's less than 0, just use 0. Okay, so we're saying use the minimum between some proposed value and 1. Okay, and use the maximum value between some proposed value and 0. Okay, and that'll prevent omega proposed from being, this will keep omega proposed within the bounds of 0 and 1. Okay, so this will be our proposal function, which I think I have here, right? So here's my propose. So like if I give it 0.8, it'll propose some value around 0.8. If I give it 0.3, it'll just propose some random value around 0.3, okay? And if I put it around 0.05, sometimes it'll propose something negative, and it'll just, in that case, it'll just propose 0. And then we use that to calculate our log probabilities. Okay, and so now I can run the whole algorithm here. So each iteration, we calculate the alpha and beta that are part of our players' distributions, okay? And each player's posterior distribution is alpha plus the number of hits, beta plus the number of outs. Okay? And again, K and N are values that exist in the global environment. We update the player S's theta value, okay? And we're just doing this for every kind of iteration. Iterations are indicated by J. So during player iteration 1, 2, 3, okay? And we're going to store all of the different theta values. We're going to just take kind of our current vector of theta values. We got, we'll have 10 of them. We've got this here. And based on this, we'll propose a new value of omega. Based on our current value of omega, we'll propose a new value of omega proposed. And then we're going to calculate the log ratio, the probability of the proposed location divided by the probability of the current location. Now, because it's the log, the division becomes a difference. So we're going to do log probability of the proposed location minus log probability of the current location. Right? So that'll give us a number. And what we're going to do is we randomly sample a random value from 0 to 1 to see if we're going to accept or reject the proposed location. If it's less than the proposed location, or less than the ratio p move, we'll accept it. If it's greater than that, we will reject it. So we're going to say if, and again, because it's the log probability, we're going to take the log of this random uniform value. If that's less than my log ratio, which is really, I guess, a log difference, okay, difference of logs, then we will accept the proposed location, okay? If not, we'll take our current one and just plug it in here, right? So if we accept it, that becomes our new omega. Otherwise, this doesn't happen, and we just take our current value, omega, and that becomes it to the next iteration of omega. All right, so I hope this works. Let me just run everything here. Okay, so it's running, and now it's done. So here we can see these are all of the different omega values. This seems pretty random. Okay, and we can ask, all right, what is a histogram of the different omega values? All right, so we're centered around 0.28. Now, what was my k and my n? Sum of k divided by sum of n. Okay, so my empirical probability of all the hits and at bats is around 0.282. So that kind of makes sense. I can ask for kind of what the mean of my omegas are. Okay, we're getting something around there, right? So all these omegas that I've generated, we can do that. We can add the density plot. We can ask what are my kind of quantiles, and then the mean of the omegas we already found. So here's our posterior distribution, and this is a random sample of all of the omega values that I've kind of generated. Okay. We can ask, what does player 1's information look like, right? So we can take, so all of the thetas that I've sampled are in this matrix thetas. I've got 15,000 rows, 10 players. So I can do thetas 1. So this is player 1. I can say, what's the mean of player 1's theta? Okay, and let's kind of compare K1 over the number of at-bats for player 1. Okay, so their empirical was this. The mean that we get is here. We can ask, what is the median theta? We get something around there. I can ask for a histogram. Oh, I'm sorry. I'm doing... Nobody stopped me. I need to do comma 1, all right? So player 1, their mean theta is 0.257. Their median theta is 0.25, is also 0.257, okay? Their empirical batting average was 0.2427. And we can do a histogram. Player 1. Okay, so here's kind of the histogram here. We can add a density. Okay, and so here's kind of the density plot there. Now, I wrote a function that will, for any player, will calculate, will create a plot, and then will also give us the number of hits, at-bats, its empirical batting average, and the kind of the mean of our posterior distribution. So for player 1, our data said this player had 118 hits, 486 at-bats. The empirical batting average is 0.242. The mean of our sampled values is 0.2578, and our median is 0.258. And this is kind of the plot that we get for player 1. I should let's say histogram main will equal histogram of sampled data values for player. Need to do paste 0. Okay, histogram of sampled data values for player 1. And let me just get rid of this. Let's make this bigger. All right, and we can see how player 2 does. So here our hits, our empirical batting average is 0.282, and our mean of our sampled values is also 0.282. Player 3, our empirical batting average is 0.238, and the mean of our sampled values is closer to 0.255. For player 4, we have this. Let me just go ahead and go through each of these players, because I think what I want to show you is, depending on the player's performance, some players had high performance. Okay, so player 7, their empirical batting average is 0.325, but again, their posterior distribution is centered a little bit closer to, say, 0.309. Okay, and that's because if we look at our thetas, or the omegas, which kind of give us a sense of what our prior distribution is, right? These are centered around 0.28. Okay, So we're centered around there, and so when a player is outperforming that, we kind of adjust it back down to around 0.28, and if the player is underperforming that, we kind of adjust it so that they're a little bit closer to 0.28. So this is kind of our posterior distribution here, right? That we have for all of our omega values along with the individual player values. And so this is, we have a fairly kind of complex model, a hierarchical model, but again, using the Gibbs sampler, we factored it out so that in each case, we only have to really sample one value. Now the omegas are more complicated, and so we're using the Metropolis algorithm to sample the omega values there. All right, let me give you your second view quiz answer. Second view quiz answer is E. E as in elephant. E as in elephant. All right. I'm probably going to run out of time to explain JAGs here, okay? But JAGs is a program that you can use. It's called, it stands for Just Another Gibbs Sampler. You would download and install this program, okay, and it allows us to kind of generate values. They're using the Gibbs Sampler, and using it's got its own separate language, but it looks quite similar to R. It's been a while since it's been updated, and it probably has been, well, I mean, the JAGs thing works pretty well. The RJAGs is how you interface with it. So JAGs is a separate program. You can look up JAGs and click this link to SourceForge. You just have to be, and you can download the program here, okay? So you would install JAGs separately on your computer. The JAGs engine, which runs in C++, would generate the values, and you interact with JAGs using the R2JAGs package. Okay? There's another package called Stan. Okay, Stan is another piece of software that will generate values via kind of Monte Carlo methods, named after the kind of Stanislaw Ulam, the pioneer of the Monte Carlo method. So anyway, let me just show you a little demo of JAGs, but we'll see how far we get, okay? There's a whole bunch of different software. So the original one was actually bugs, Bayesian inference using Gibbs sampling, and then that stopped being supported, and then so they shifted to JAGs, but now JAGs is no longer supported. Although the interface still works, and R2JAGs continues to be updated. So if you look up R2JAGs, that was updated in August of 2021. So R2JAGs keeps getting updated, whereas just the base JAGs engine, that's kind of set, hasn't been updated, and it's still being used, okay? Now, the nice thing about JAGs is that you don't have to figure out all of these conditional distributions. You kind of just, you specify how your model is set up, okay? So you describe the hierarchical model using the bugs language, okay? And again, JAGs is based off of bugs, which is no longer supported or developed. And so you have to kind of read a little bit on, it looks a lot like R, okay? But it's a little bit quirky. And of course, the website's broken. All right, let me, so this is how our model would be set up. Okay, so it looks familiar, but it's a tiny bit different, okay? So all of the parameters that just are pre-specified, I'm just going to throw here. Okay, A omega is 3, B omega is 7, K is 300. These do not come. These are not randomly generated. Okay, and then alpha and beta are based off of omega and K, right? So where does omega come from? And so this feels strange because the values are all kind of defined out of order, and that's okay. The bugs language will figure out what order, the hierarchy here, okay? So the tilde means it's generated from this random distribution, okay? So we're kind of accustomed to writing like that in our notes, but not when it comes to generating values, okay? So here we're gonna say omega is a value generated from the beta distribution, okay? And this beta distribution is defined by shape parameters A omega and B omega. In this case, I could have just written d beta 3 comma 7. I could have done that. You can also specify, right? So the arrow is used for assignment, and then the tilde is used for random variable generation as far as the bugs language goes. Okay, so we're going to say omega is generated from this. All right, and here we're going to say, okay, for each player, okay, for S in 1 through the number of players, okay, the player's theta value comes from d beta, alpha comma beta, and then we have j at bats, all right, so we're going to need a vector of at bats, okay, we're going to say each observation in here comes from a Bernoulli distribution. Okay, and so you actually have a Bernoulli, d Bernoulli, using this particular theta, right? And so this is how we specify the model in the bugs language here. All right, so that their website's down. And then what you do is you specify this thing. All right, and now this is not legitimate R code, right? Like if you tried to run this, it would break, right? R is not going to accept this. But you wrap it, you just take all of this code and you wrap it inside a function, right? And when you do that, R is not even going to bother trying to like evaluate anything. It just says, okay, and then we call this our Bayes model. All right, so when you specify the model in R2JEGS, you just wrap it in a function. It's not a function that we would ever run in R, but this is how R2JEGS expects it, okay? You could also kind of write a separate text file to do it. And so here I guess line by line, we've defined each of these things, okay? So let me just kind of skip through that because I explained it a little bit. And so then what you have to do is you have to provide all of the values that appear inside this model, okay? So if you look at I guess I haven't run it here on this machine. We have to provide, so here's the model, okay? And here this model makes reference to this term, number of at-bats. And so you need to provide those values. We've got number of at-bats, number of players, along with the data y, okay? And so as far as the data goes, we're going to say the data that JAGS needs is going to be a list, and we give it the names, y, number of at-bats, number of players, okay? Now these are going to be objects that exist in the R environment, okay? So within the R environment, I've got y, the number of at-bats is this, the number of players is this. So these are values that will exist in the R environment, and we provide that. We also tell the JAGS model what parameters we want it to sample. Okay, so we want to have it sample generate values for theta. Theta is a vector of length 10, and we want to have it generate sampled values for omega. Okay, and so we would run that. And I think we're going to be out of time. So we'll do this, I guess, on Wednesday. We'll take a look at this on Wednesday and just see the results there. But so we'll wrap up here. Today's final view quiz answer is the letter C. C as in cat. C as in cat. I gave you the other two, right? Okay. C as in cat is our last view quiz answer. And that will be it. Okay? So maybe I'll see you guys on Wednesday. If not, have a good holiday. All right? I'll be here on Wednesday, but if you decide to take off, I understand. Have a happy Thanksgiving, and we'll see you guys whenever we see you guys. All right? Have a good day.